Now that we have learned that hydrogen ion ingress is the basis for all hydrogen damage, we turn our attention on the most important types of hydrogen damage mechanisms. These include 1. Hydrogen embrittlement and/or blistering. 2. Stress-oriented hydrogen-induced cracking, SOHIC. 3. Sulfide stress cracking, SSC. 4. Stress corrosion cracking, SCC. And 5. High-temperature hydrogen attack, HTHA. Knowledge of these hydrogen damage mechanisms will be invaluable to the ASME B31.3 subject matter expert in the coming decade due to all of the attention on hydrogen as a new and valuable energy source. The different mechanisms all depend on ion migration to affect the steel, but different mechanisms relate different hydrogen formation, ion life, and hydrogen ion migration to the associated damage mechanism. So let's review these different hydrogen damage mechanisms.
Well, first, let's take a look at the types of hydrogen damage we will be reviewing during this tech talk. First, there will be hydrogen-induced cracking, HIC, which is just the hydrogen embrittlement blistering that we just went over in the previous tech talk. Next, we find stress-oriented hydrogen-induced cracking, SOHIC. Sulfide stress cracking, SSC, stress corrosion cracking, SCC, and last, high temperature hydrogen attack, HTHA. These are the main types of hydrogen attack that we will need to be aware of. We won't do much on the first one because we just spent a tech talk on it, but we should start looking at stress-oriented hydrogen-induced cracking. Even though stress-oriented hydrogen-induced cracking is a form of hydrogen embrittlement, it has one other characteristic that hydrogen embrittlement does not require. Stress-oriented hydrogen-induced cracking requires stress, whereas hydrogen embrittlement does not. Further, stress-oriented hydrogen-induced cracking will produce cracks that are perpendicular to the direction of the stress, and they may be, as shown, layered or stacked. They are very likely to be in the parent metal near a weld due to the residual stress from the weld. Further, they do not produce blisters, so there is no real warning that anything is going on at the weld. And since there are no blisters, and SOHIC is a very quick, very dangerous type of hydrogen embrittlement, the result could be a very quick, catastrophic, and unexpected failure. In SOHIC, the hydrogen ion migrates, and because of the stress, there could be voids or dislocations in the steel that are now further enhanced as far as volume goes and is very favorable for the hydrogen ion migration. So, in summary, SOHIC is different than HIC, hydrogen-induced cracking, in that the stress affects the direction, the number, orientation with respect to each other, layered, whereas in HIC, stress does not play a role at all, and the orientation is based on the direction and shape of the inclusions in the steel. Next, we look at sulfide stress cracking, which always happens, obviously, in the presence of sulfides, most notably hydrogen sulfide. Well, in this case, with sulfide stress cracking, the sulfides do play a role in the hydrogen damage mechanism. The sulfides actually prevent the hydrogen ions generated from the water, which many would normally recombine to hydrogen gas and just be flushed off. But the sulfide plays a role in preventing that, which increases the number and amount of hydrogen ions for permeation into the steel. And so with H2S, hydrogen embrittlement, which is what this is, can occur much faster thanks to the sulfide ions. So let's look at the role of the sulfide ion in hydrogen generation. From the chemical formula where iron, H2S, and water is present, we see that it goes to Fe, iron, sulfide, and the hydrogen ion negative plus H30. We take the iron sulfide hydrogen negative ion and it goes to FeSH plus, but it yields up 2 electrons. And those electrons go straight to the remaining H2S, and that produces H2 plus 2SH. And that H2 is the key because it's in wet hydrogen, and there is the generation of the hydrogen ion from H2S and water and iron in solution. So what we have for sulfide stress cracking is generally a sulfide, an H2S, that is an hydrogen ion generator for the embrittlement or the cracking of the steel. So not only do we have hydrogen present, we have a generator that generates hydrogen, which supports accelerated hydrogen embrittlement. And that is the mechanism for sulfide stress cracking, which can result in very fast embrittlement failure. And the source of the H2S in the industry? Well, for the most part, that would be sulfate-reducing bacteria, which is present in oil-producing formations, pipelines, and in some process equipment. Although stress corrosion cracking does not have to do with hydrogen, for this tech talk, we're looking at hydrogen specifically. What creates a stress corrosion cracking environment involving hydrogen? Well, whenever corrosion occurs, there is, especially in lower pH and lower applied redox potentials, that facilitates the evolution and enrichment of hydrogen at the site of corrosion. And this enriched hydrogen can then promote hydrogen embrittlement. Same thing we talked about in the last tech talk. One specific place you can find this type of environment generating hydrogen would be crevice corrosion. Corrosion in a cell that is isolated from the rest of the process in a piping system or in the system where the steel is exposed to factors that create crevice corrosion. In a crevice corrosion state where under the cap of the crevice corrosion there is a continuous pH drop due to the corrosion and the redox potential underneath that barrier, and that drops the pH, causes hydrogen generation. Hydrogen can then enter directly into the steel during the crevice corrosion activity. That can result in hydrogen embrittlement. For this high temperature, the situation is a little bit different. This time hydrogen migrates through the metal lattice into the metal itself, where because of high temperature, carbon ions are available. From the chemical equation governing the reaction, we see 8 hydrogen plus carbon plus 3 iron C. We yield 2 methane plus 3 Fe ions. It is that 2CH4 that we're interested in, because what happens is as the hydrogen ions go through the lattice and into the steel, the available carbon forms with the hydrogen to form methane gas. And that methane gas does exactly what the hydrogen gas did in the dislocations, this time at high temperature, but the presence of gas continuing to expand and pressure up these voids causes brittle fracture. Same thing. This concludes this Tech Talk on hydrogen damage mechanisms. So let's do a quick review of what we learned on this topic of hydrogen attack methods. Although there are other types, these are the 5 most common that will be impacting for the SME. Well, the first and most important point probably is that all hydrogen damage is caused by hydrogen ion migration or ingress into the steel structural lattice. Stress-oriented hydrogen-induced cracking, SOHIC, is really related to embrittlement, but it is impacted by stress, and the cracks are then oriented accordingly to be perpendicular to the stress field. Sulfide stress cracking is caused by the presence of sulfides, and these sulfides do promote hydrogen generation and also affect the surface of the steel to result in very accelerated hydrogen embrittlement. These are often caused by the sulfate-reducing bacteria. Next, we had and studied stress corrosion cracking, which is SCC, and this results from the pH and the redox potential that's created by the corrosion activity in the corrosion cell, and this hydrogen can cause hydrogen embrittlement. Next, we had high temperature hydrogen attack, HTHA, which is caused by the, again, hydrogen ion migration at high temperature into the steel lattice, where it finds available carbons to form methane gas, and the methane gas can lead to intergranular and void high pressure, which leads to embrittlement. This completes this module on different types of hydrogen attack. This small complimentary video is actually a part of a larger module on full hydrogen training available as part of a complete B31.3 subject matter expert course, which is available at the link shown on the course description pie chart. I'm Michael Shelton, and I thank you for watching this small video on the types of hydrogen attack. See you next time.